Hi everyone, welcome to this session which will be about the new steel design features for the European market in Advanced Design 2024. My name is Thibaut Frété, I'm a structural engineer at Goetech working on product specification and validation. So first we will see a new verification for the shear buckling of a web. Then I will show you the new buckling definition and buckling results on call-for members. Then we will move on to some new welded connections for hollow profiles, and eventually you will see our improved presentation of the deflection results. So let's begin with the shear buckling of the web. This check is introduced in the Eurocodes 3 part 1.5 related to plated elements, and this verification can be critical for deep I-beams, which are commonplace in bridge construction, for example. And because the moment is taken by the flanges, the web gets very thin, and this makes the web prone to plate buckling from shear force, also known as shear buckling. So the first thing that Advanced Design will do is to check if this verification is required or not. And for that, it will compare the width to thickness ratio of the web with some limits defined in Eurocode 3 part 1.5. There is a lower limit for an unstiffened web, and if you have stiffeners along the web, you can use a higher limit. And if you are below that limit, then you have what they call a stocky web. So you don't need to actually worry about a thing, and you can check the shear resistance according to Eurocode 3 part 1.1. But if you are above that limit, then you have a thin or slender web, and you need this extra check from part 1.5. So we can see right away that they make a difference between a stiffened and unstiffened plate, because it's common to add stiffeners along the web. They can be vertical stiffeners or transverse stiffeners, or they can be horizontal or longitudinal stiffeners. And these stiffeners will mitigate the shear stresses that develop diagonally in the web, because instead of dealing with a long and high web, you will be dealing with smaller panels with smaller shear stress. And this solution of introducing stiffeners is actually cheaper than using a massive web, because the element remains lighter. So this verification is about comparing the design shear force with the resistance for shear of the member. And the resistance for shear is coming from the web, but also from the flanges. But to be honest, it's mainly coming from the web. To estimate the contribution from the web, first you need to estimate, to find out kappa W factor, which is a buckling factor of the web. It depends on the relative slenderness of the web, based on a sigma I stress related to the dimensions of the plate itself, but also on the type of transverse stiffener that you have at the beginning of the plate. This stiffener can be rigid or non-rigid. So a rigid stiffener will lead to a better contribution from the web. But to qualify as rigid, there is a condition to meet. So, for example, you will often need a pair of double-sided stiffeners, or even an inserted vertical I section at the beginning and end of the plate. Advanced Design will also compute the shear buckling coefficient, K tau, which depends on the distance between the stiffeners, so the transverse stiffeners and also the longitudinal stiffeners. But keep in mind that Advanced Design 2024 only allows for transverse stiffeners and that they qualify as non-rigid. That was for the contribution from the web, but there is also a contribution from the flanges. But it's usually so small that it's neglectable. So, first of all, the flanges can only contribute if they have some capacity left after taking the bending moment. That's why Advanced Design will compare the design bending moment with the resisting moment of the flanges alone. And if the flanges can actually contribute, then you need to find out a C length which is the distance between the hinges that will form along the flanges, because there can be no contribution past those hinges. But when you have that, when you have capacity left of flanges and the C length, and you can estimate the contribution from the flanges. You will add that to the contribution from the web to get the entire shear buckling resistance of the web plate. So I'll show you how it works in advanced design. So let's focus on this steel bridge for a minute. So here I've got some deep I-beams with a very thin web. If I just run the finite element calculation just to check the internal forces first, I would get some shear force diagram with a peak shear force on the middle support, but I've also got some bending moment there, so maybe the flanges won't be able to contribute. So from there, I would, if I were to run the steel design on this beam, I would, here I'm getting the message about the shear buckling verification being required, because the web is definitely not stocky. So from there, I would activate the verification and probably introduce some stiffeners. So to place these transverse stiffeners at the moment, longitudinal stiffeners yet, there are many ways you can input a number, you can define some spacings, or you can use a graphical definition. Let's say you want to place these stiffeners right below the applied point forces. You can click them on the model, and in the command line you can see the list updating. And when you're done, you press enter and the table is automatically updated. So if I run the steel design again on the same beam this time, the verification was passed, and you can actually check the results either in the simplified shape sheet. You see the last two lines are about the shear buckling of the web, but I personally prefer the detailed version of the shape sheet, because there you can track every single intermediate value. So now let's comment on that. So first of all, you have the information about the result location. Here, it's on an intermediate support where we have shear force and bending moment. So first of all, we check if the verification is required, and we see here the limitation of a stiffened web, because we did have stiffeners. So the web, we are above, way above the limit, so we have a thin web for which this verification, the shear buckling verification, is required. So the K2 coefficient is computed depend on the distance, the spacing between the stiffeners. You combine the K2 with the sigma stress, and that gives us the relative slenderness of the web, lambda. And with this lambda, you can read the kappa W buckling coefficient from the table. And that gives us the contribution from the web. Then you move on to the flanges. And the first thing is to find out if the flanges can actually contribute. And here they can, because their resistance is higher than the design bending moment. But they will only contribute outside of a C length, the distance between their hinges. That gives us a rather small contribution from the flanges. So when you sum up the two, you get the entire resistance for shear buckling from the web plate, which is higher than the design shear force, and the check is passed. There is also an additional verification where you check the interaction between the shear force, the bending moment, and the potential axial force in the web. But this check is only meant if the previous verification, the shear buckling of the web, got you more than a 50% utilization. And you also need to have some bending moment actually going through the web, because if the moment is taken by the flanges, as is often the case, well, usually you won't worry about that. But anyway, this check is performed in advanced design, but here the design bending moment was small enough to be taken by the flanges, so there was no problem there. So now let's see the improved definition of buckling length for cold form members. So when it comes to cold form design, you can either run a second order analysis on the member. So this can be done in advanced design using the advanced stability feature. But starting last year, we introduced this interaction, this alternate interaction formula, where the buckling resistance from the axial force covers all buckling modes, flexural, torsional, but also torsional flexural buckling, and also the effects of lateral torsional buckling on the bending moment. So, by the way, this formula is from the current version of the Eurocodes 3, but there will be an update at some point, and this formula will clearly show the bending moment in each plane. You will see my and mz, and the coefficients will also be different. Instead of 0.8, there will be a 0.85, but we don't have a publication date yet. So the buckling effects cover the well-known flexural buckling, where the axial force produces a deflection of the member that can lead to failure. So this flexural buckling uses a critical length that can be defined in the buckling dialog. But then comes the torsional buckling. The axial force produces a twist of the section. And then you've got the flexural torsional buckling. And these two effects are usually governing for cold form members, because you are dealing with open sections with very low torsional resistance and a significant offset between the shear center and the centroid of the section. And here you see in the torsional buckling critical force, we've got all that. We've got the torsional constant, we've got the warping constant, and I-O covers the distance to the shear center. And it uses a critical length of its own that you can now define in advanced design. And then for the flexural torsional buckling, basically you will reuse the critical force that has been computed just before. So now in advanced design 2024, you can accurately define each of these critical lengths. And you can do the same for the lateral torsional buckling length, because we've got an updated dialog where you can place restraints on each flange. You can access every single parameter. And in this case, the critical bending moment will be computed according to Annex I from the Eurocode 9. So this part is meant for aluminum, but it also applies to steel members. This is what we are using for monosymmetric cold form members. So the MCR formula is way more complex, because it still uses a C1 and C2 coefficient, but now you've got the introduction of a C3 coefficient that you can define, as well as other parameters to account for the degree of asymmetry of the section. So let's see how it works in advanced design. Let's work on this steel building for a moment. So it's made of cold form members. We've got channels, we've got a sigma section, but I will focus on this omega section there, which is the top chord of the truss. And so it's definitely a hot section there, and I want to design it not with the advanced stability feature, which would run a second order analysis on the member. I want to use instead the alternate formula, for which I will define all buckling length and the lateral torsional buckling length. So here the buckling length for flexural buckling and the one for torsional buckling. So for flexural buckling in plane, I will use the distance between the vertical supporting members, so that will be 3/16. And for the out-of-plane buckling length, I would rather use a smaller distance, like the distance, the spacing between the purlins. So that would be 158. But for the torsional buckling, I would use the buckling length in the symmetry plane. So that would be the vertical plane, again, 316 meters. So I will find that in the dialog. So flexural buckling in plane, we had 316. Flexural buckling out of plane, 158. And for torsional buckling, I was using the buckling length in the symmetry plane, so 316. Now moving on to the lateral torsional buckling definition. You see in this dialog, you can define restraints, you can define the C3 coefficient. Here, it was decided to place some batten plates all along the member with regular spacings and close enough to actually prevent, to turn it into some sort of closed section, and actually it was enough to neglect the lateral torsional buckling effect. So in this dialog, I would simply check this box and consider a continuous restraint to ignore the lateral torsional buckling effects. Now I can run the calculation and check the steel design results. And with the finite element calculation being performed, I can run the steel design analysis on this member and check the results in the simplified shapesheet. But again, I would prefer the detailed version to get all the information on the buckling parameters. So you can see there all the details, so we will comment on that. So for the flexural buckling, well, you compute a critical force based on the critical length that we've defined. You get a relative slenderness and then a phi coefficient for which depends on the buckling curve that will give you the value of the alpha parameter. And by the way, in the current version of Eurocodes 3, you won't be able to find the omega section there. But we've asked our contacts, and turns out for a hat section, you should consider curve B with a corresponding alpha of 0.34. So that's how you get the phi coefficient. That gives you the buckling factor in the main plane. Do the same for the secondary plane with a different critical length. And as you can see, the flexural buckling was not much of an issue there, because at worst you've got a 10% reduction on the resistance. But then you've got the torsional buckling effects, which depend on the torsional and warping resistance, which are very low there, and also this IO parameter depending on the distance between the center of gravity of the section and its shear center, which is very far away, giving you a significant value for IO and lowering the critical force for torsional buckling. This is the 316 meter that we've defined on the model. So you've got, again, a relative slenderness, a phi coefficient, and a buckling factor, which is way lower there. We've got almost a 50% reduction on the resistance. And it's pretty much the same for the torsional flexural buckling, which introduces a beta coefficient, and again, critical force, relative slenderness, phi, and kappa. And these are the four coefficients that you could see in the detailed shapesheet. So the two first are for flexural buckling, in plane, out of plane, and the one for torsional and torsional flexural. And from there, you can perform the actual buckling verification involving the buckling effects from the axial force and the lateral torsional buckling effects on the moment. But here, remember, they were neglected, so we've got a kappa LT of 1. But for the buckling, we are considering the minimum value of the 4 kappa that we had. So 0.51, giving us a 90% work ratio, and this was the exact same utilization we've got in advanced design, except in advanced design we got that in instant. And just a note regarding the American market, this version 2024 of advanced design also supports design of code for members according to the American standards. So you've got basically all the checks from the standards and a dedicated section library. So now let me show you the new welded connections that we have for hollow sections. So now you will be able to handle the typical truss connections with 1, 2, or even 3 diagonals that will be square hollow or rectangular hollow sections. That way you can deal with all the configurations described in the Eurocode 3. And as for the top and bottom chords, they can be square, rectangular, hollow, or even eye shapes. So the connection design will be handled by the connection module, either running within advanced design or as a standalone application. So all checks from the Eurocode 3 part 1.8 will be performed with a corresponding work ratio. And of course, it comes with a detailed calculation report with all the information from intermediate values to article reference. So let me show you how it works in advanced design. So I've got some typical truss with a square hollow sections. So if I want to define some welded connection there, I will find them here with, let's start with 2 diagonals. So basically in the command line, you are told to click the main beam, then the first and second diagonal, and you've got your connection object. And should you have 3 diagonals, it will be same process, the main beam and the 1, 2, and 3 diagonals. And from there, you can run the analysis. And you run the joint design. So all the internal forces are coming from the finite element calculation, and you've got your various checks and work ratios. So of course, it comes with a calculation report. And in this report, you get, all the assumptions, connection views, and all the checks with intermediate values and article reference. So now let me show you our improved presentation of the deflection results. By that, I mean that the shape sheet will now mention the deflection values, not just in ratio, but in millimeters as well, which is way easier to understand and to process for the user. We're also printing the result location, which can be in span, usually for a beam, or at the extremity of the member for a column. So when choosing the results, make sure to select values. That way you will get the deflection in unit length, so commonly in millimeters. So let me show you how it works in advanced design, and for that let's get back to our steel bridge from before. So if I select the beam we've analyzed, in the deflection tab of the shape sheet, I can check the deflection. So I'm interested in the in-plane deflection. It's 19.3 millimeters. I also get the value in the ratio, but the value in millimeters is more helpful. And it's definitely a deflection in span, which is legit for beam. And if you want that graphically, when choosing the results, make sure not to ask for a ratio, but switch to values, and that way you will get the deflection in unit length. So here we're getting a 19.3 millimeters in span, just as expected. So that concludes our presentation. I hope I kept you interested. Together we've seen the new verification for shear buckling of the web, the improved definition of buckling length for cold-formed design, some new welded connections for hollow profiles, and the improved presentation of the deflection results. And by the way, be aware that you can submit your projects for the Advanced Design Awards, and make sure to check out our dedicated website, advanceddesignaward.com. So thank you all for your attention, and I hope to see you soon. Bye, everyone. So hi, everyone. I'm here if you have any question. Place them in the chat. Right. There doesn't seem to be any questions, so I will end the recording now. And well, thank you for attending, and see you soon. Bye.